Welcome back everyone. In this lecture I will continue the representation theory of sl2c. So, I will first recall what we did in the last lecture. So, what we did, we started with actually finite dimensional irreducible representation of capital V and established a very nice basis of that capital V. So, let me just recall. So, say V is actually finite dimensional irreducible representation of sl2c. Okay. So, if you recall, so what we did, so step 1, so we actually looked at the action of H on V and then took mu to be eigenvalue of this H. Because we are working over complex numbers, there exists an eigenvalue and then we take V to be eigenvector corresponding to this eigenvalue. In particularly, we have H V equal to mu V. Okay. So, then if you denote V gamma by the gammath eigenspace of this H. Okay. So, that means by definition this is those W in V such that H W is given to be gamma W, where gamma is in C. So, then we realized that if you apply x on this V gamma, so that should be subset of V gamma plus 2. Okay. And then if you apply y on this V gamma, so that should be subset of V gamma minus 2. Okay. This is something we verified directly using the commutator relations. Okay. So, now if you go back to this mu, so then what we realize, because if you apply x on V and then x square on V and so on, then at some point we have to stop. So, we take k to be minimal such that x power k V is actually non-zero and x power k plus 1 V is 0. So, why such k exists? Because x v, x square v and so on, they all corresponds to distinct eigenvalues of H. Okay. V will corresponds to mu, then x v corresponds to mu minus 2 and x square v is mu minus 4 and so on. So, this is all H eigenvalues. So, that actually says that because we are working inside finite dimensional representation. So, there must exist some k such that x power k plus 1 v is 0. So, now you choose k minimal, so that this x power k v is non-zero. So, that all this mu, mu minus 2 etcetera, mu minus 2 k sorry mu plus 2, mu plus 4 and so on, mu plus 2 k, all of them are eigen values of this operator H acting on capital V, but mu plus 2 k plus 1 is not an eigenvalue. Okay. So, in particularly what we did, we replaced lambda by this mu plus 2 k and then V naught by this x power k V. Then we realize that H acts on V naught as lambda V naught and then x acts on this V naught as 0. Okay. So, this kind of vectors we called maximal vector. So, once we have this maximal vector, so then what we immediately did, we looked at how this y acts on this V naught. So, you look at V naught and so on. So, then as before, there will be some r such that y power r V naught will be non-zero, but y power r plus 1 V naught is 0. Again using the earlier argument, there exists r in G plus such that this happens. Okay. So, that implies we immediately saw that if you take this span of this V naught, y V naught etcetera, y power r V naught. So, that is indeed sl2 invariant. So, that makes this into a whole space because V is being irreducible. Okay. And then we saw that with this respect to this nice basis, okay, if you call V I equal to y power I V naught, then we had this very nice action of this sl2c on this V I. Okay. So, that is given by the following identities. The first one, H acting on V I be lambda minus 2 I V I, and second is Y acting on V I will be V I plus 1, and third thing is X V I is nothing but I times lambda minus I plus 1 V I minus 1. So, where we understand that V minus 1 is 0, okay, and this is all true for all I greater than or equal to 1. So, I greater than or equal to 0. So, using these formulas we concluded that H acts diagonally on capital V, and then from this formula 2 you can easily see that Y acts nilpotently on capital V. Similarly, X also acts nilpotently on capital V. Okay. So, observations, H acts semi simply or diagonally on capital V, and then X and Y both act nilpotently on capital V. Okay. These are all the observation, and not only that, this lambda has to be R, and all the eigen values must be R, R minus 2 etc., minus R plus 2 minus R. So, these are all the eigen values, and the corresponding eigen values eigen spaces must be one dimensional, that is what we saw. Okay. So, these are all the eigen values of H acting on acting on V, and if you take this V R minus 2 I, this is spanned by just y power I V naught, which is just V I. Okay. So, this is what we saw in the last class. But now the question is, this is actually allows us to define map from isomorphism classes of finite dimensional irreducible representations of SL2C to these non-negative integers. But the question is why this map is surjective. So, we still have not established any irreducible representation explicitly corresponding to given non-negative integer. So, that is what we are actually going to do. Okay. So, what we do? So, we actually going to prove this following theorem. So, this is actually kind of classifies completely all finite dimensional irreducible representations of SL2C. So, in one side what we do, we take this set of all isomorphism classes of finite dimensional irreducible representations of SL2C. Okay. So, then on the other side what we do, we take this non-negative integers. So, what is the map? So, map is very natural, you take this class V and then send it to dimension V minus 1, because recall the relation, this R has to be dimension V minus 1. Okay. Basically, this R captures all the information about this capital V. And it is clear that this map is actually well defined, because if you take two isomorphic irreducible representation, the dimensions will be same. So, this number will be same. Okay. So, what we need to check? We need to check this map is surjective as well as injective. To prove this map is surjective, there are many ways actually one can check. So, I will leave it to you to check the following thing very abstractly without actually getting into the actual representation. What one can do? One can actually define abstractly. You start with the space, okay, which is of dimension R plus 1, take V to be just a span of V naught etc. V R, okay, V 1 etc. V R. So, then what you do? You just define the action of SL2C on this abstract vector space using the formulas, okay. H V I equal to lambda minus 2 I V I, and then Y V I equal to V I plus 1, and then X V I to be I times lambda minus I plus 1 V I minus 1. So, if you define the action of sl2c using these formulas again for I greater than or equal to 0 and then with the convention that v minus 1 is 0. So, then you can actually prove that this defines well defined action of sl2c on capital V. Okay. So, I leave it to you to check. So, this defines well defined action of sl2c on capital V. So, what one supposed to actually check? So, we have to check if you take the commutators of these corresponding elements. For example, if you take the bracket x y, then you should be able to get h, that is the thing you have to check. For example, you can easily see that the basis if you fix to be this v naught v 1 etc. v r. So, then the matrix of x with respect to this basis you can see that. So, this I goes to I minus 1. So, in particularly for 0 it is 0. So, x v naught is 0. So, this is going to be just 0 0 0 and then x v 1 it is going to be 1 times r minus 1 plus 1 times v naught. So, this is just r v naught. Okay. So, that is going to be r here and then 0 elsewhere and then x v 2 you can see that this is twice r minus 2 plus 1 v 1. So, that is twice r minus 1. Okay. So, this is twice r minus 1 v 1 0 and everywhere else is 0. Okay. So, it is clear that on the diagonal all the entries will be 0, only the first off diagonal entries will have entries and all other things will be 0. Okay. So, this is going to be this a strictly upper triangular matrix, okay, with the entries only in the first off diagonal, okay, on the top of the diagonal. So, that is very clear. Similarly, if you look at what will happen to this matrix of y with respect to the same basis. So, this will be again lower triangular matrix. So, it is strictly lower triangular where the entries will be here on the first off diagonal which is below this diagonal entry. Again what will be the matrix of H? The matrix of H will be just your diagonal matrix because H V I is nothing but lambda minus 2 I V I. So, this will be just R minus 2 etc. minus R plus 2 minus R, all other entries will be 0. Okay. Now, what we need to check, if you take the commutator of these two, okay, then you need to check this has to be exactly equal to the matrix H. Okay, this is something you need to check. Similarly, you have to check for all other commutator relations. So, I will leave it to you to check. So, it is not very hard, it is just basically a matrix multiplication with these specific matrices. So, that indeed proves that given any R, so you have this R plus 1 dimensional space on which this SL2C is actually acting. So, you have a representation of SL2C. Now, it is not hard to prove that this V must be irreducible. So, that is just follows from following argument. So, if you have this well defined action on this capital V, so then let us say W is actually a proper submodule of V. Okay. So, then what will happen? So, let us say W is actually non-zero module. Okay. Let us not assume anything about proper. So, let us say it is a non-zero module. Then there will be a W inside this W, okay, which will be again eigenvector of H, because H is acts on W, okay, because W being sl2 submodule, okay, this is let us say sl2 submodule. So, this H must act on W. So, in particularly there exists W in W such that HW will have this eigen value mu. Okay. So, this mu has to be one of the eigen value as before. Okay. This mu has to come from R minus 2 etcetera minus R plus 2 and then minus R, because the eigenvalues of entire eigenvalue H eigenvalues of this capital V is this list. So, it has to come from that. So, in particularly note that the eigenspaces corresponding to this each eigenvalue, they are all one dimensional. So, this W must be some scalar times whatever that Vi. Okay. This mu has to be some R minus 2i and this W must be some scalar times Vi. By replacing that scalar, we can assume to be this is exactly Vi. Okay. So, that proves this Vi is inside W. Okay. Now, look at the action of x and y. So, if you actually use, if suppose Vi is there, if you use the action of y, then from this Vi you will be able to go to Vi plus 1. Similarly, from Vi plus 1 you can go to Vi plus 2 and so on. Okay. So, since this Vi is in this W, by applying YVI you get Vi plus 1. So, that has to be in W. Similarly, that proves that by applying another Vy we get Vi plus 2 is also in W and so on. So, that proves that Vj is in W for all j greater than or equal to I. Now, what happens to what happens if you apply x on Vi? If you apply x on Vi, you can see that this actually reduces the indices up to some non-zero scalar. This I times lambda minus I plus 1, it will be never 0 for this lambda coming from, this lambda is R basically. So, it will be never 0. So, that says that if you apply x, then x Vi, which will be some non-zero scalar multiple of Vi minus 1, that has to be in W. So, that proves that Vi minus 1 will be in W and that proves that Vi minus 2 will be in W and so on. So, that proves that Vj will be in W for all j less than or equal to I. So, this actually implies all Vj are in W for all j from 0 to R. That proves that capital V is subset of W. Okay. So, that proves that V is W. So, by choosing this one eigenvector of H, we can see that by applying repeatedly x and y, we get all other eigenvectors. Okay. So, that way we recover this capital V entirely from one eigenvector. So, that makes this W equal to V. So, that proves that V must be irreducible if V actually satisfies these conditions. Okay. So, this is abstractly proving that given non-negative integer, there exists actually irreducible representation whose dimension is just R plus 1. Okay. That actually proves that this map is surjective. Okay. This map is surjective. So, from the same argument you can also see that this map is injective. Why? Because suppose we have, let us say, two representation, irreducible representation of sl2C such that the dimension of V minus 1 is same as dimension of W minus 1, then that will imply that dimension of V equal to dimension W. Okay. Now, we know that there exists a basis for this capital V such that it is given by this V naught, V 1 etcetera V r. Similarly, there exists a basis for this W which is also given by W naught, W 1 etcetera W r, where the action of H, X, Y, they are all given in this formula, okay, this star. So, that means you can just simply map this V I to W I, and then we can define a map from V to W, call it phi, and it is easy exercise to see that this phi is an isomorphism and phi is also SL2 homomorphism, okay, SL2 module homomorphism. So, that proves this phi must be actually gives isomorphism between this two SL2 modules. This is SL2 module isomers. So, that proves that the map that we have defined is indeed injective. So, that means that we have established bijective correspondence between the set of all isomorphism classes of finite dimensional irreducible representation of SL2C and this non-negative integers. Okay. So, we know like completely all information about a given finite dimensional irreducible representation of SL2C using our analysis. Okay. So, but what I want to do, like I want to give actually very explicit construction of this representation. Okay. So, for that we need to actually recall how SL2C is acting on this two variable polynomials. Okay. So, using that action one can actually see that if you take any homogeneous space, so that will be actually corresponding to irreducible representation. Okay. So, I will actually leave all the checking as exercise. So, basically you need to establish a basis. On that basis the basis elements of SL2C acts the way that we have seen in general finite dimensional irreducible representation. Okay. So, what we do to make our life easy, we denote using this isomorphism for D in G plus. So, whatever that irreducible representation that we are getting from D, we denote it by V D. Okay. So, that will be the isomorphism classes of the isomorphism classes of SL2C irreducible representation that having D plus 1 dimension. Okay. So, that unique isomorphism class we call it VD. So, whenever I say VD, that is actually irreducible representation of SL2C whose dimension is D plus 1. Okay. So, now what we are going to do? We are going to explicitly construct these representations. So, for which we are actually going to take this infinite dimensional space. So, call it CUV. So, this is just a polynomials in two commuting variables. Okay. Polynomials in two commuting variables UV, again over complex numbers. Okay. So, now what we do? We define this SL2 action on this polynomial ring or polynomial algebra. Okay. So, how it is given? It is given as follows: if you take some element for P in CUV, you take XP to be just U times dou P by dou V. Okay. And similarly, YP to be V times dou P by dou U. And now, once you are given X and Y action, it is easy to create what is H action. So, recall H is nothing but the bracket X Y. So, in particularly the H action of on P has to be U Okay. So, basically x y p minus y x p. Okay. So, you can just work it out and then see what it is. So, basically y p will be v dou p by dou u, and then x will be u dou of this divided by dou v. Okay. Minus similarly v dou by dou u dou p by dou v. So, if you do the computation, then what we get? So, dou of dou v dou p by dou u is nothing but dou p by dou u plus dou by dou v dou p by dou u. Okay. So, similarly dou by dou u dou p by dou v is nothing but dou p by dou v plus u dou by dou v dou p by dou v. Okay. Sorry, here it is v. So, then if you plug in back, and then you can see that h dot p should be equal to u times this. So, u dou p by dou u plus u v dou by dou v dou p by dou u, and then minus v times dou p by dou v minus u v dou by dou u dou p by dou v. Okay. So, you can actually, these two things are same. So, this will get cancelled. So, you get h p by u dou p by dou u minus v dou p by dou v. Okay. So, you can just use the commutator relations to get how h will act on this CUV. So, this is indeed actually tells you that so there is a unique way actually this is going to act if you know the action of h and y. Now, it is not very hard to prove that like this is indeed giving you action of SL2C on this CUV. So, that I will leave it to you to check. Okay. So, check that. So, this gives us action of SL2C on CUV. Okay. Now, what is more, if you take this what is called this homogeneous spaces. Okay, what is homogeneous spaces? So, that is spanned by elements of this form. So, take V of d to be span of all u power I v power j, where the degree of this monomials should be all same. Okay, that should be equal to d. So, this is those I j in G plus such that I plus j equal to d. So, you take this V of d inside your CUV. Okay. So, then it is easy to check this V of d is indeed SL2 submodule of CUV. Okay. Again check this V of d is SL2C submodule of CUV. Okay. By establishing very explicit basis, so which is already given here, you can see that this V of d is indeed SL2C irreducible representation. Okay. So, this is all something I would like to leave it to you to check. This is all now very explicit calculations. Okay. For example, if you take the dimension of this V d, so given I, this j must be d minus I. So, you can see that the choices of for I is just 0 to d. Okay. So, that makes this V of d has dimension d plus 1, and then using the formulas you can explicitly calculate and then see how this x, y and h acts on this basis elements, and then it will be clear like how you can actually get something related to what we have already established. Okay, that I will leave it to you to check. I will actually continue with the lecture later. Okay, I will prove this complete reducibility for this finite dimensional representation of SL2C in the next lecture. I will stop here.